Today, we're going to explore a fundamental and pretty counterintuitive tension that exists in almost any complex system. Now, there's a really common assumption we all tend to make that making a system more efficient is always a good thing. The idea that making something faster, leaner, and more productive also makes it stronger, more robust. But what if that's not just wrong, but the exact opposite of the truth? What if the very act of perfecting a system for a predictable world is precisely what makes it shatter in an unpredictable one? So that's the central paradox we're looking at. How can a series of smart, rational decisions, all aimed at making a system better, actually pave the way for its total collapse? To get to the bottom of this, we first need to be really clear about what we're talking about. So what is a system? At its most basic, it's just a set of parts that interact with each other to achieve some kind of goal. Think of a company, a supply chain, a power grid. Really, anything where the key isn't just the parts themselves, but how they interact. And the way those components connect really defines the whole system's architecture. We can group them into two main types. In a loosely coupled system, the parts have some independence. There are buffers, a bit of slack between them. But in a tightly coupled system, everything is interdependent. There is absolutely no slack. In a tightly coupled system, you can think of the connections as being rigid, almost immediate. It's like a line of dominoes. A change in one component instantly and directly affects the next one down the line. There's just no room for error. A loosely coupled system, on the other hand, has buffers built in between its parts. Now, these buffers can be anything: extra inventory, spare time in a schedule, or even people with overlapping skills. Their job is to absorb shocks. So a problem in one area doesn't immediately cascade through the entire system, because that buffer acts like a cushion. For instance, imagine an office where one team can't start their work until another team finishes a specific report. That's a tightly coupled process. A single delay brings everything to a standstill. Now contrast that with an office where both teams work from a shared, constantly updated pool of documents. That's loosely coupled. Work can continue even if one specific piece of information is held up. On a normal day, both systems look like they're working just fine, but one is secretly much more vulnerable to even a tiny disruption. But here's the crucial thing. A system's structure isn't fixed. It's not set in stone. It actually changes over time, and it's driven by some really powerful incentives. And probably the most powerful incentive of all is the constant pressure for more efficiency. In a management sense, efficiency is all about the systematic elimination of what's called waste. This could be anything from excess inventory sitting in a warehouse to the time people spend waiting between tasks. The concept that stands in direct opposition to this is resilience. Resilience isn't about peak performance in a perfect, predictable world. It's about a system's ability to absorb the unexpected, to bend when something goes wrong instead of just breaking. And this is where the fundamental conflict becomes so clear. The very things that an efficiency mindset labels as waste, like extra inventory, spare time, or redundant capacity, are the exact same things that give a system its resilience. They are the buffers. So the relentless drive to optimize a system is, by its very definition, the process of removing its shock absorbers. As you strip away those buffers, the system's whole structure starts to change. What was once a flexible, loosely coupled system becomes more and more rigid, more tightly coupled, where every single piece is directly and unforgivingly linked to the next. This change doesn't happen overnight. It's the slow, creeping result of many small, perfectly rational decisions that add up over time. We can actually watch this happen using a simple, abstract model of a component delivery system. Okay, let's walk through this. Imagine a supplier providing parts to a manufacturer. In step 1, the initial state, the manufacturer keeps a big inventory on hand. That's their buffer. In step 2, a manager makes a smart local decision. Reduce that inventory to cut storage costs. It's a win. It looks great on their report. In step 3, this success gets noticed and the behavior accumulates. Everyone starts removing their buffers to get similar results. The final outcome in step 4 is a brand new global state. The entire system is now incredibly efficient, just in time, and dangerously tightly coupled. Think about a delivery service. To be more efficient, they replace their generalist drivers, who know the whole city, with specialists who only know one specific route. Day to day, things get faster, but a buffer of skill and flexibility has just been removed. So when one specialist calls in sick, there's suddenly a hole in the service that a generalist could have easily filled. A local optimization created a hidden global vulnerability. So, after this whole optimization process is complete, the system looks perfect. On the surface, it's flawless. There's no visible waste. Every component is perfectly synchronized. It is the very model of a high-performance system. But this perfection is an illusion. The system's stability now depends entirely on the world around it being perfectly stable too. It's been engineered to run flawlessly, but only as long as nothing, absolutely nothing unexpected ever happens. It has become brittle. This brings us to a really important idea from the sociologist Charles Perrow, called a normal accident. What Perrow argued is that in systems that are both highly complex and tightly coupled, major failures aren't just possible, they're basically inevitable. They are a normal emergent property of the system itself, because you can't possibly foresee every single interaction that could lead to a breakdown. So let's go back to our component delivery system. A minor disruption happens, something completely ordinary, like a delivery truck gets a flat tire. It's not a catastrophe, just a small, everyday delay. But remember, our system is now highly optimized. It's tightly coupled. That inventory buffer that used to exist, the one that could have easily absorbed this kind of delay, it's gone. And because there is zero slack in the system, that minor delay doesn't just slow things down, it brings the entire production line to an immediate, complete halt. The next station has no parts. Work stops. And it doesn't just stop there, because every single part of the system is now interdependent. The failure cascades. The halt at the manufacturer forces the supplier to stop their lines. The problem spreads backwards and forwards as one tiny localized issue triggers a complete system-wide collapse. This really illustrates the core insight here. The catastrophe wasn't caused by a big mistake or a faulty part. Everyone involved, from the truck driver to the managers who cut inventory, was acting rationally. The failure was an emergent property of the system structure, a structure that was deliberately and intelligently designed for maximum efficiency. So what this reveals is a fundamental trade-off. Optimization is about creating predictability and high performance within a known, expected set of conditions. Resilience, on the other hand, is about being able to handle surprise and survive in unknown conditions. And here's the final takeaway. A system cannot be perfectly designed for both of these goals at the same time. The more you push for one, the more you sacrifice the other. And understanding that unavoidable trade-off is the key to understanding not just how systems work, but ultimately why they fail.